All right, so today, let's dive into some really fascinating math.
Oh, yeah.
Have you ever tried solving an equation like x phi a sop plus 1 equals 0? You're basically searching for a number that, when you square it and then add 1, you get 0.
Right.
The catch is you can't actually find that number within the real numbers that we usually
Oh,
use.
you hit a wall.
Yeah, and that's where things get super interesting because it kind of nudges us towards this world of complex numbers
Exact.
and something called the fundamental theorem of algebra.
It's like you're trying to find a solution, but it's nowhere to be found within the number system you're familiar with.
Right.
And that's precisely why the fundamental theorem of algebra is such a game changer.
Yeah.
It basically guarantees that no matter how complicated a polynomial equation gets,
Okay.
even with those complex coefficients, there will always be at least one solution in the realm of complex numbers.
All right, so to make sure we're all on the same page, can you give us a quick rundown of what a polynomial is?
Sure.
And those complex numbers, too, while we're at it.
All right, so a polynomial is kind of like a mathematical recipe with variables and coefficients. You can think of it as combining ingredients like x, xo, and so on, each multiplied by some number, and then adding or subtracting them.
Okay.
And complex numbers, on the other hand, they kind of expand our numerical playground beyond just the real numbers. And they introduce this imaginary unit I, where I equals -1, which opens up a whole new dimension of possibilities.
Okay.
And every complex number is this mix of a real part and an imaginary part, a plus b, where a and b are real numbers.
So today we're doing a deep dive all about unpacking the fundamental theorem of algebra, and we're going to be using the Wikipedia page as our guide.
Sounds good.
We'll explore its history, uncover its profound implications, and even peek into the different ways that mathematicians have tried to prove this cornerstone of mathematical thought.
Okay.
What's so important about this theorem?
Well, what's truly mind-blowing about the fundamental theorem of algebra is that it guarantees that the world of complex numbers is a complete self-contained system when it comes to solving polynomial equations.
Oh, wow.
You'll never need to invent some new, exotic type of number to find a solution. They're all nestled within the complex number system, just waiting to be discovered.
So it's like complex numbers are the ultimate destination for solving these equations.
Exactly.
We don't need to venture into uncharted mathematical territory.
Exactly. But this realization didn't just appear overnight.
Right.
It has a rich and fascinating history full of twists and turns. It's like a mathematical detective story.
I love those. So tell me, where does the story begin?
No.
Who were the first to stumble upon this fundamental truth?
Well, early whispers of the theorem can be traced back to mathematicians like Peter Roth. And Albert Gerard Roth, as early as 1608, hinted that a polynomial equation of degree n might have n solutions.
Okay.
Gerard in 1629 was even bolder.
Oh.
He stated that a polynomial equation of degree n does have n solutions, but he added this curious caveat.
Okay.
Unless the equation is incomplete, meaning if no coefficient is equal to 0.
Oh, interesting.
But when you dig into his work, it seems like he believed it held true in all cases.
So even back then, they were sensing that there was this deep connection between the degree of a polynomial and the number of solutions.
Yes, but their ideas were still in their early stages.
Hmm.
And it took quite a while for a truly rigorous understanding to emerge.
Right.
In fact, even the great Leibniz made a misstep in 1702. He asserted that certain polynomials like xo plus o, is a non-zero real number, couldn't be factored into simpler polynomials with real coefficients.
But wait, didn't Euler prove him wrong?
Yes, you're absolutely right.
That's where things get really interesting.
Euler, being the mathematical genius, he was swooped in and proved Leibniz wrong.
Yeah.
He showed that xo plus o can actually be factored into the quantity xo plus a times the square root of 2 times x plus a, closed quantity, times the quantity xosis minus a times the square root of 2 times x plus a. This was a pivotal moment because it shattered this misconception held by one of the most prominent mathematicians of the time.
Yeah.
And Euler's insight paved the way for a more complete understanding of the theorem.
It's incredible how these early mathematicians built upon each other's work, sometimes even challenging giants like Leibniz.
Yeah.
So we have these initial intuitions and Euler's crucial correction, but the quest to formally prove the fundamental theorem of algebra continued, didn't it?
It did. The journey wasn't over.
Yeah.
Mathematicians like D'Alembert Euler himself, de Fontenay, Lagrange, and Laplace all took their shot at proving the theorem.
Wow.
But their attempts, while insightful, shared a common flaw. They kind of took for granted that solutions already existed and focused on proving what form those solutions must take.
So they were assuming the answer without fully proving it.
Precisely. They were working under the assumption that solutions existed in the form a plus b, where a and b are real numbers.
Okay.
But the challenge was to prove that those solutions absolutely must exist in the first place.
I see. That's a subtle but important distinction.
Yes. So who finally cracked the code and delivered the first rigorous proof? That honor goes to an unexpected hero, an amateur mathematician named Argand.
Oh, wow.
In 1806, he published the first complete and rigorous proof of the fundamental theorem of algebra.
Wow.
And what's even more remarkable is that his proof considered polynomials with complex coefficients, not just real ones, making it even more powerful.
An amateur mathematician beating the big names to the punch, that's a fantastic story.
Yeah.
It's a good reminder that groundbreaking discoveries can come from anywhere.
Right.
But I'm sure Gauss, with his reputation for thoroughness, couldn't resist adding his own contributions, right?
You know, Gauss, he couldn't stay away.
Yeah.
Even though Argand had already nailed the proof, Gauss went on to publish 2 more proofs in 1816. And he even revisited his original proof in 1849. It seems that this theorem really captured his imagination.
Wow.
And interestingly, the first textbook to include a proof of the theorem was Cauchy's Cours d'analyse de l'École Royale Polytechnique in 1821.
Okay.
And you know what proof he chose?
What's that?
Argand's.
Oh, wow.
However, he didn't give Argand credit for it, which is a bit of a shame.
That's a reminder that the history of mathematical ideas isn't always straightforward.
Yeah.
Sometimes credit isn't given where it's due, and contributions can be overlooked.
Right.
But back to those proofs, did any of them actually tell you how to find the solutions? Or did they just prove that the solutions must exist?
That's a great question. Most of these early proofs were what we call non-constructive.
Oh.
They brilliantly demonstrated that the solutions exist,
Okay.
but didn't provide a recipe for actually finding them. It's like knowing there's treasure buried somewhere, but not having a map to pinpoint its location.
So it was like a mathematical, trust me, they're out there situation.
Exactly. But this lack of a constructive approach didn't sit well with everyone.
Right.
Weierstrass, in the mid-19th century, issued a challenge to find a constructive proof. A proof that not only shows that the solutions exist,
Okay.
but also provides a method for calculating them.
That sounds like a tall order. Did he succeed in finding one himself?
He did. In 1891, Weierstrass presented his own constructive proof, ingeniously combining the Durand-Kerner method with the homotopy continuation principle.
Yeah.
And he wasn't alone in this pursuit. Another constructive proof emerged in 1940, developed by Helmuth Nezer, which his son Martin Nezer later simplified in 1981.
It seems like the fundamental theorem of algebra has captivated mathematicians for centuries, sparking a quest for increasingly elegant and insightful proofs.
Yes.
We've uncovered its fascinating history and the key idea that it makes complex numbers the ultimate solution space for polynomial equations.
Right.
But the Wikipedia article mentions some different but equivalent ways to express this theorem.
Yeah.
Could exploring those shed even more light on its meaning and importance?
Absolutely. Let's delve into those different formulations and see how they enrich our understanding.
Okay, let's do it.
All right, so one way to state the theorem is every polynomial with real coefficients and a degree greater than 0 has at least one complex root.
So even if we stick to real numbers for our polynomials coefficients, we might need to venture into the world of complex numbers to find a solution.
Exactly, and from there we can actually jump to a broader statement.
Okay.
Every polynomial with complex coefficients and a degree greater than 0 also has at least one complex root.
Now, that's interesting. We're saying that even if the coefficients themselves are complex numbers, we're guaranteed to find at least one complex solution.
Right.
But how do we get from the first statement to this more general one? It seems like a big leap.
It's a clever trick involving complex conjugates.
Okay.
Imagine you have a polynomial with complex coefficients. We can create a brand new polynomial by multiplying the original by its complex conjugate.
Okay.
Remember, complex conjugate just flips the sign of the imaginary part.
Right. And when you multiply a number by its conjugate, you always end up with a real number.
Exactly.
So this new polynomial would have real coefficients.
Exactly. Now, according to our first statement, this new polynomial with real coefficients has at least one complex root. This root must be either a root of our original polynomial or a root of its conjugate.
Okay.
And if it's a root of the conjugate, its own conjugate will be a root of the original polynomial. It's like a 2-for-1 deal.
Wow. So either way, we're guaranteed a complex root for our original polynomial, even if it started with complex coefficients.
Yes.
That's a really elegant way to connect those two statements. But the theorem doesn't stop there, does it? The Wikipedia article mentions something about factorization.
Yes, the fundamental theorem of algebra can also be expressed through the lens of factorization.
Okay.
It states that any polynomial of degree n with complex coefficients can be factored into this form. C times the quantity x minus r sub 1 closed quantity times the quantity x minus r sub 2 closed quantity, and so on, until times the quantity x minus r sub n closed quantity, where C is a complex constant and r sub 1, r sub 2 up to r sub n are the roots of the polynomial.
Let me make sure I've got this right. We have n roots matching the degree of the polynomial, and they're all neatly tucked into these x minus root factors. It's like disassembling a complex machine and finding its basic components.
Precisely. This factorization really underscores the idea that every polynomial, no matter how complicated, can be broken down into these fundamental building blocks.
Yeah.
And if a root shows up multiple times, that's what we call a multiple root, with its multiplicity being the number of times it appears.
This factorization view is really powerful. It shows that even the most intricate polynomial can be reduced to these simpler pieces.
It is.
But are there any practical implications to this factorization idea? Does it help us understand anything beyond the structure of polynomials?
It absolutely does. This factorization form leads to other fascinating and equivalent statements of the theorem.
Okay.
For instance, it implies that every polynomial with real coefficients can be broken down into factors that are either linear, which is degree 1, or quadratic, which is degree 2.
So if we stick with real coefficients, our building blocks are a bit more limited. We
Yeah.
might need those quadratic factors to handle roots that don't fit nicely into a linear x minus root form.
That's the idea. These different formulations highlight this intricate dance between real and complex numbers,
Right.
and how the fundamental theorem of algebra beautifully connects them. It's like they're two sides of the same coin.
It's mind-boggling how a seemingly simple statement about polynomial equations leads to such profound insights and connections.
I know, it's amazing.
We've explored the theorem's evolution, its significance as a bridge between real and complex numbers,
Right.
and even delved into its factorization implications. But I'm curious about how mathematicians have gone about proving this fundamental truth.
Okay.
I know we won't dive into the nitty-gritty details, but could you give us a taste of the different approaches?
Absolutely. Given its fundamental nature, there are numerous ways to prove the theorem. One approach uses real analytic proofs, which stay within the realm of real numbers and cleverly manipulate them using properties like continuity and the intermediate value theorem.
So it's like they're playing a game within the rules of real numbers to indirectly show that complex roots must exist.
Precisely. It's a brilliant example of mathematical ingenuity.
Yeah.
Then we have complex analytic proofs, which harness the power and elegance of complex analysis.
Okay.
These proofs leverage tools like the maximum modulus principle, Liouville's theorem, and the argument principle.
Those sound incredibly sophisticated. I have to admit my complex analysis is a bit rusty.
Oh, yeah.
Could you give us a simple analogy for one of those principles just to get a taste of what they're about?
Sure. Imagine the maximum modulus principle like a hill.
Yeah.
The highest point on that hill cannot be found in a valley. It has to be on the edge, the boundary of the hill.
Okay.
Similarly, the maximum modulus principle tells us that a non-constant complex function reaches its maximum absolute value on the boundary of a region not inside.
That's a great way to visualize it. It's
Yes.
like the complex function is climbing to its maximum value on the edge of its domain.
Exactly.
It makes those complex analytic proofs a bit less intimidating.
Why?
But I understand there are other approaches, right?
Yes.
What about these topological proofs I've heard about?
Yes. Topological proofs bring in concepts from geometry and topology to shed light on the theorem. One such approach utilizes winding numbers,
Okay.
which might sound a bit abstract, but are actually quite intuitive.
Winding numbers. I'm intrigued. Can you give me a simple explanation? I'm a very visual learner.
Imagine you're walking your dog around a pole. The winding number tells you how many times the leash wraps around the pole as you complete a full circle.
Okay, that makes sense. So it's like counting how many times we wind around a central point. I can see how that could be applied to curves in the complex plane.
Exactly. Winding numbers provide this visual and intuitive way to grasp the fundamental theorem of algebra. They connect this abstract world of polynomials to this more concrete realm of geometry.
Yeah.
But the story doesn't end there. We also have algebraic proofs, which delve into more abstract algebraic concepts like splitting field and Galois theory.
Now, those sound a bit more intimidating. Can you demystify them a bit for us?
Think of splitting fields as expanding our number systems to accommodate all the roots of a particular polynomial. It's like building a bigger house to accommodate all your friends.
Okay.
And Galois theory, Well, it's like a powerful lens that helps us understand the symmetries and relationships between different kinds of number systems. It's a beautiful but abstract area of mathematics.
It's amazing how this one theorem can be approached from so many different angles,
I know, it's really cool.
using tools from analysis topology and even abstract algebra.
Right.
It really highlights the interconnectedness of mathematics, doesn't it?
Absolutely. It's a testament to the elegance and power of mathematics that such diverse approaches converge on the same fundamental truth.
Yeah.
It speaks to the unity and harmony within the mathematical world. But beyond the proof techniques themselves, the fundamental theorem of algebra has some intriguing consequences known as corollaries.
Okay.
Would you like to explore some of those?
I'm all ears. Let's see what other hidden treasures this theorem holds. So we've journeyed through the history of the fundamental theorem of algebra, explored its different faces, and even peeked into the diverse ways mathematicians have proven it.
Right.
But you mentioned something about corollaries consequences that stem from this theorem. What are some of the ripple effects of this fundamental truth?
One of the most significant takeaways is that complex numbers act as what we call the algebraic closure of the real numbers.
Okay.
It's like they complete the real number system, providing the perfect playground to solve any algebraic equation that originates from the reals.
So if we start with real numbers and want to find solutions to our equations, we never have to venture beyond the realm of complex numbers.
Exactly.
It got us covered.
Another fascinating corollary relates to factoring those polynomials with real coefficients.
Okay.
Remember how we talked about breaking them down into linear and quadratic factors?
Yes, those linear factors capture the real roots, and the quadratic factors are needed to handle those pairs of complex conjugate roots.
Precisely.
It's like fitting puzzle pieces together.
And this has some interesting consequences. For example, it tells us that any polynomial with real coefficients and an odd degree must have at least one real root.
That makes sense. If all the roots were complex, they'd have to come in conjugate pairs,
Right.
leading to an even number of roots. But that wouldn't match up with the odd degree of our polynomial.
Right.
It's like trying to fit square pegs into round holes. It just doesn't work.
Exactly. There's one more corollary I'd like to highlight,
Okay.
one that bridges the gap between algebra and calculus.
All right.
It turns out that any rational function, which is just a ratio of two polynomials with real coefficients, can be broken down into simpler parts.
Okay, that sounds intriguing. What kind of simpler parts are we talking about here?
Think of it like taking apart a complex machine and finding its basic components. We can break down these rational functions into polynomial functions plus rational functions with a very specific form.
Okay.
Some look like a over the quantity x minus b, closed quantity raised to the power of n, where a and b are real numbers and n is a natural number. Others take the form the quantity x plus b closed quantity over the quantity x unsards plus cx plus d raised to the power of n, where a, b, c, and d are real, and c minus 4d is negative,
Okay.
ensuring that the denominator doesn't have any real roots.
So we're essentially dissecting these complicated rational functions and finding these fundamental building blocks.
Exactly.
But why is this important for calculus?
This decomposition has huge implications for integration. It means that any rational function with real coefficients can be integrated using elementary methods.
Oh, wow.
It's like having a toolbox with all the right tools to solve a specific set of problems.
That's incredible. Who would have thought that a theorem about polynomial equations would have such far-reaching consequences in calculus?
I know, it's amazing.
It really shows how interconnected different areas of math are.
Absolutely.
Yeah.
And it highlights the power and beauty of the fundamental theorem of algebra. It's not just a statement about polynomials, it's like a gateway to deeper understanding across multiple mathematical domains.
This deep dive has been truly enlightening.
It has.
We've gone from simple equations to the fascinating world of complex numbers, explored the history and evolution of a groundbreaking theorem,
Yeah.
and even uncovered its profound consequences. It's amazing how a single idea can lead to such a rich tapestry of mathematical understanding.
It's a beautiful reminder that mathematics is full of surprises and hidden connections.
Yeah.
We started by wondering about solutions to a simple equation, and we ended up exploring the algebraic closure of numbers,
Right.
the structure of polynomials, and even the integration of rational functions.
It makes you wonder, though. We now know that complex numbers are a complete system for solving polynomial equations originating from the real numbers. But could there be an even larger, more expansive number system out there?
Right.
One where we could find solutions to equations that can't be solved with complex numbers alone, It's a mind-boggling thought.
It certainly is, and that's the beauty of mathematics. It always leaves us with more questions, more avenues to explore, and more mysteries to unravel.
So, as we wrap up this deep dive, we're left with a sense of wonder and a thirst for further exploration. The fundamental theorem of algebra, with its elegant simplicity and profound consequences, serves as a reminder that mathematics is a journey of discovery full of unexpected connections and endless possibilities.